All right, so continuing along with the idea from the periodic table, here is an example of oxygen with isotopes. So again, if you were to look at the periodic table, oxygen has an atomic number of 8. So that means that there are 8 protons. But you're also going to find out when you're looking at things, you'll get some different numbers, different isotopes. Here we have oxygen O16 and O18, and what that means is the 16 would be the mass number, and so again, because oxygen has a atomic number of 8, that would mean it would have 8 protons, and the mass number is 16, so all you do is subtract the protons from the mass number, which would also give you 8. So that means it has 8 neutrons. The isotope oxygen 18 would then have, again, because the atomic number is 8, that never changes. 8 protons, you subtract that, then that you would actually have 10 electrons. I'm sorry, 10 neutrons. The other thing I should mention, which is why I misspoke there, is that when you see um, an atom and it has no charge on it, what that is telling you that the number of electrons is equal to the number of protons. So what they're showing you, the blue balls in these pictures, is that there are 8 of those also, that actually equals out the charge. Okay, so again, let's just repeat. The atomic number is the number of protons, and typically the number of electrons if it's neutral. Um, and then the mass number is the number of protons plus the number of neutrons. So let's talk about radioactive isotopes. There are several. These are ones that actually degrade over time. And so, I want you to think about it. We talk about radioactivity actually causes damage, causes cancer. But I want you to know that it also can be very useful for certain things. So radiometric dating is one. You might have heard of carbon dating. That is a type of radiometric dating. Carbon dating is used to date earlier fossils. Carbon 12 is your typical isotope, but carbon 14 is radioactive, and it has a half-life. It degrades into carbon 12 over a period of time. That half-life is known as 5,640 years. So as a living creature, you are taking in carbon, and the carbon that's in the atmosphere is in a quantity, um, um, certain amount of carbon 14 to 16 um, in your system. So you're bringing both those in. You're bringing in mostly the normal one, but you're also bringing in a little of the radioactive isotope. Once you pass away, once you're gone and you're not taking it anymore, what happens is the carbon in your system starts to degrade, and so they can look at that amount. The other way we use it is as tracers, typically in medical tracers. And so here, what you're seeing is they're using some kind of radioactive isotope to trace um, systems in your body. And so what will happen is they'll inject you with a radioactive isotope. Again, the amounts that they use and the half-life of these are typically very, very quick. They break down very readily. Um, and what happens with a lot of these is that these isotopes actually will attach to cancerous tissue, cancers, and we'll talk about cancer later. And so it'll attach to those and then show up on something like that picture on the bottom right, which is actually a PET scan. So showing some cancerous throat tissue. They can do this with prostate tissue. They can do this with ovarian cancer that has moved. So often they'll do a PET scan with a radioactive tracer to try to see if cancer has metastasized. All right, so this is a picture where they're checking this little girl's exposure to radioactivity. This is out of the Campbell book, and I don't know what is scarier, the fact that she might have been um, exposed to radioactivity, or the fact that these guys are very scary with their smiles on their faces. So yeah, as a parent, I would be really, really concerned. But what I want to talk about is radioactivity. It has some, we have nuclear power plants, and that's run off of a uranium, a radioactive isotope, which has a very, very long half-life. And so one of the problems we have is using nuclear power. That is often called an environmentally safe type of energy. And reality is, environmental factors probably pretty low until there's an issue. And I want to mention there's been issues. So I don't know if you've heard of Chernobyl. Chernobyl's in Russia, and in 1986, it had a meltdown, and nearly 30 to 40 more times more fallout than the Hiroshima and Nagasaki nuclear weapons we used. The United States dropped on Japan. And only you'll see 56 direct deaths, which doesn't sound like much, but reality is that is not including all of the deaths and illnesses due to cancer. And so very unfortunate. And actually, HBO has a Chernobyl series, a special, which is very worth watching. I learned a lot. I wasn't going to watch it. I know about that disaster, but my wife wanted to watch it, so we watched it. It was very good, very graphic. There's language and nudity, but definitely worth watching if you have the time. All right, so I know what you're thinking. Hell, it's Russia. Who the hell cares? Um, uh, you know, Closer to home, 3 Mile Island. You may not have heard of this. 3 Mile Island is in the United States, and in 1979, there was a partial meltdown. No direct deaths or injuries, but again, a release of uh, radioactivity into the environment. And you're thinking, well, where the hell is 3 Mile Island? Well, it's right next to Hershey, Pennsylvania, and where you get your chocolate. And I love the picture of the cows. They're like, what? So yeah, you're all going to die. Just let you know that. But then again, we've just had a more recent one, 2011. It's been 10 years now. Hard to believe. Um, but Fukushima Daiichi nuclear power plant in Japan. They basically had one due to a tsunami that flooded an earthquake, which then causes the tsunami that flooded their power plant. Triggered by the 8.9 earthquake, one of the big ones. And unfortunately, the U.S. urged that they clear a 50-mile area. They only cleared 6, and they couldn't get in to stop it. And what they ended up doing is they needed somebody to go in there, and they were going to assign people. And this is what heroes are made of. There's a bunch of older people who did not have family or kids. They volunteered, knowing that this was probably going to cause major, major health effects, if not death. Um, but anyway, so the reason I bring these up is, luckily for us, we don't have to worry about this because we don't live in Japan, we don't live on 3 Mile Island, and we do not have nuclear power plants here in California. And I pause and I pause. I don't know if you realize, but we do. And San Onofre is one. We have a local one. If you ever drive down the freeway, you can actually see it um, south of us. And it's closed now, but it still has radioactive waste there. But luckily for us, in California, there aren't any earthquakes. So Did I mention you're going to die? So good luck. Microwaves, another form of energy. These are very low waves, but I just want to go on record that you guys are guinea pigs. What are the long-term effects of microwaves? We don't know. We assume they're pretty safe. They're fairly broad bands, which typically don't cause any problems. You all have microwaves at home, I'm sure. Do you actually read the directions? I'm sure you don't. You know, people think, oh, I know how to use a microwave. Reality is they're giving off the waves. If you read the directions, they will tell you many, many things. One is that you are not supposed to stand in front of the microwave while it cooks. So I want you to think about where your microwave is when you're cooking. Is it one of the raised ones where you open it up and it's at face level? Is it on a counter where it's near your waist? Um, One of the things it tells you is after it turns off, you wait for an amount of time before you open the door. That lets the microwaves balance and dissipate. But most of you, it's still running as you open it up because you you need your food fast. You can't wait another 4 seconds. Um, and microwaves have not been tested for long term. The only they used to think that police officers using radar guns used to get testicular cancer, and people are like, "Well, how the hell did that work?" The idea is the gun was pointed at the car as it comes by to get the speed, and then when they were done, they would rest it on their lap, which means it's basically pointing at their private parts. And they thought that would lead to testicular cancer. That study has been disproved. That is not true. The one thing that they do know that microwaves can actually cause retinal damage, eye damage. So I love the fact that they put a nice little bright light in there while your food is cooking, so you can lean over, see it, and then go blind. In theory, though, if your microwave is in good shape and it does not leak, you shouldn't have any issues. Also, phones give off waves. You can see, and you can see this picture is old because who the hell has a phone that looks like that anymore? But we hold our phones to our head, and teenagers use phones probably more than older people. And one of the problems they found out is microwaves. I'm not saying cause damage, but by holding the phone up against your head, what they noticed is changes in the cellular metabolism. There are changes, things are sped up. Now, whether that's good or bad, we don't know. It's a long term study. Welcome to the study. You are the guinea pigs. And now some of you are telling me, oh, no, Mark, I have an earpiece. And so it's not a problem. I keep my phone on my lap. Yeah, so say hello to your children with all their issues. So good luck. You're all going to die. Just kidding. Uh, anyway, so let's talk about energy levels. The last thing, the way that and we'll do this again with the periodic table, but the way that the energy goes in is the electrons will fill these shells or orbitals. Okay, so there's a shell where the electrons are all flying, moving around, that they're kind of held in this energy level. And then within that, there are orbitals, which is the pathway these electrons will take. And we're not going to go into all the details of the different ones, the two, S's and P's and all that stuff. That's not important for biology. But we do want you to know that the first two electrons will go into that first shell. And then after that, a third electron added to an atom will actually go into the second shell. And that second shell can take up to 8. And then the third shell also will go up to 8. So what I want you to realize is these electrons fall and they're trying to become as stable as they can. So here's what I need you to understand as we go forward with bonding on our next one is that to make an atom happy is you're always trying to fill that outermost shell. That will make them more The word happy means stable. And so we will be taking a look at that. So here we have the actual, again, kind of numbers, the 1s and 2s. The s's will hold 2 electrons. The p's will hold 8. And I'm not, again, worried about all that so much, but it's important when we talk about this to understand bonding and why things bond the way they do. And so, again, when we do the periodic table, we'll talk more about that. So we will end